In this video, I'm going to be working through some more examples of partial fraction decomposition. This video contains some more complicated examples involving repeated factors and irreducible quadratic factors. All right, so let's start with this example. So again, we look at this and we say to ourselves, this is a polynomial divided by a polynomial, so I'm going to think about trying to use partial fractions. And as always, the first thing we check is the degree of the top and the degree of the bottom. The degree of the top is 1, the degree of the bottom is 2, so we don't have to do any long division. We can go straight to our decomposition. But the difference here between the types of problems I was talking about in the previous video is that we have a repeated factor. If I factor x squared minus 2x plus 1, I don't get two different linear factors. I get the same linear factor twice. I get x minus 1 squared. So the way that we decompose this is we have repeated fractions up to the power that we have. So we have x minus 1 squared. So we're going to have two fractions involving x minus 1 to the first power, and x minus 1 squared. If it had been x minus 1 cubed, then we would have had three factors, all with constants on top, but progressively getting higher and higher powers until we get up to the power that we have. In this case, we just have a squared, so we get two fractions. But notice that even though the bottom of this fraction is quadratic, the top of the fraction is still just a constant. So what you put on the top of the fraction is based on the factor, not just how many times it's been repeated. So even though we have a quadratic on the bottom, we still just have a constant on the top. Now, as usual, we want to multiply both sides by this full denominator to clear our fractions. So we're going to multiply both sides by x minus 1 squared to clear out those fractions. So on the left-hand side, we get 3x. On the right-hand side, when we distribute, we get a times x minus 1, and then just b. Now, one big difference when we have these repeated factors is that the plug-in trick that we talked about in the previous video partially works, but it doesn't completely tell us all of our coefficients that we need. In this case, we can plug in x equals 1, and that will tell us what b is. On the left-hand side, I get 3. On the right-hand side, I get b. So of course, that means that b is equal to 3. But there's nothing easy that I can plug in here that's going to tell me what a is. So instead, what we use is the method of equating coefficients. So what we do is we multiply out both sides of this equation. So we get ax minus a, and then b we already figured out was 3. And then we write this as a polynomial, ax plus negative a plus 3. And on the left-hand side, we can think of that as 3x plus 0. And again, this needs to be true for all values of x, which means the coefficients have to be the same. So 3 has to be the same as a, and 0 has to be the same as negative a plus 3. Either of those tell us that a has to work out to be 3. So that's the method that we use. In addition to using the plug-in trick when we can, we have to equate coefficients to figure out our missing constants. All right, so our decomposition is done. We figured out that this fraction can be rewritten as 3 over x minus 1, a over x minus 1, plus b over x minus 1 squared. So that's 3 over x minus 1 squared. Now that first fraction is going to be a simple u equals x minus 1 substitution. U equals x minus 1, du is equal to dx. So that's just going to give us 3 times the natural log of x minus 1. And then we do the same simple substitution for the second fraction, but that's not going to give us a natural log. That's going to give us the integral of 3 divided by u squared. That's 3u to the negative 2, which is going to be 3 times u to the negative 1. And my u was x minus 1. So that's what I get when I integrate that. Sorry, I divide by the new power, 3 times u to the negative 1, divided by negative 1, which makes that coefficient negative. So it's not always going to give us natural logs here, especially when we have higher powers. So I got to be careful there. All right, next one. So here we don't have a repeated linear factor, but what we do have is an irreducible quadratic factor. So if we factor that bottom of that fraction, we can factor out an x, but then we get x squared plus 4, and x squared plus 4 here is what we call irreducible. It cannot be factored without bringing in imaginary numbers, and we don't do that in this class. So our decomposition tells us that we're going to get two fractions because we have two factors. Remember, one fraction per factor. And on the top of the linear factor, we just have a constant, just like we've been doing. But on the top of the irreducible quadratic factor, that's when we have a linear term. So we have bx plus c, where we have to figure out what b and c are. Now we're going to multiply both sides by this denominator. We'll multiply both sides by x times x squared plus 4. That'll clear out those denominators, get rid of those yucky fractions. So we get 8 equals a times x squared plus 4, and bx plus c times x. Now again, there's only one thing we can plug in here, and that would be x equals 0. It does help though. Plugging in x equals 0 tells us that 8 equals a times 4, which means that a equals 2. But for the rest of this, we're going to have to multiply this out and equate our coefficients. So on the left-hand side, we just have 8. On the right-hand side, we have a, which we now know is 2. So we have 2x squared plus 8 plus bx squared plus cx. So if we write both sides as a polynomial, left-hand side is 0x squared plus 0x plus 8. The right-hand side is 2 plus b x squared plus cx plus 8. And we equate coefficients of equal powers of x. So 0 has to be the same as 2 plus b, 0 has to be the same as c, and 8 has to be the same as 8. Well, that last one doesn't really tell us anything, but the first two tell us that b has to be -2 and that c has to be 0. So here's our decomposition. Our integral looks like a over x, a we figured out was 2, plus bx plus c divided by x squared plus 4. We figured out that b was -2 and that c was 0, so that's minus 2x divided by x squared plus 4. Now, we've seen these many times. We know how to integrate 2 over x, natural log of absolute value of x, no big deal there. But what about 2x over x squared plus 4? We're going to talk more about how to deal with generally these irreducible quadratic factors, but this is an easy example because this one lets us substitute u equal x squared plus 4. du is 2x dx. We have that 2x dx, we just have a minus sign. So this is going to be minus the natural log of the absolute value of x squared plus 4 plus c. So in this case, that irreducible quadratic factor wasn't too nasty to deal with. We're going to see some worse examples as we go on in this video. All right, so here again, we have a repeated linear factor. So what we could do is we could do partial fractions and rewrite this as 2x divided by x plus 2 squared equaling a over x plus 2 plus b over x plus 2 squared, and work out what a and b are and proceed like we did in the first example. But I want to suggest an alternate strategy for problems like this. This one doesn't actually require partial fractions. And one of the things that we should be learning in this chapter is how to apply the right strategy for the right problem and try to not use the most complicated tool that we know if there's a simpler way to do it. And in this case, the simpler way to approach this problem is to simply substitute u equals x plus 2. And if we do that, we get du equals dx. So this looks like this might be a good substitution to use because that turns my denominator into just u squared, and dx and du are the same thing. But what do I do with that 2x on the top? Well, one of the tricky things that we can do with substitutions is we can rewrite that equation u equals x plus 2 as x equals u minus 2, which means the top of this fraction is 2 times u minus 2. Now, the advantage of doing this is that since my fraction now looks like 2u minus 4 divided by u squared, I can break that up into two simpler fractions, 2u over u squared minus 4 over u squared, or 2 over u, and then I'll write this as 4u to the -2. So that's going to give me 2 natural log of the absolute value of u. Antiderivative of u to the -2 is u to the -1 divided by -1, which turns that 4 into a plus 4, plus c, and then we substitute back in. 2 times the natural log of x plus 2, plus 4 times x plus 2 to the -1, plus c. And that is tricky, and so we might not think of that, right? This approach here with the partial fractions, this still works. It's just harder if we don't see the tricky substitution way to do it. So you've got options, and in a lot of problems that you'll see, you will have options. There won't just be one way to do it. It's up to you to try to recognize what is the most efficient, most effective way to approach the problem. Okay, back to partial fractions. So this is an example where we don't actually have to do a partial fraction decomposition, but it gives us a chance to practice what we do when we have an irreducible quadratic factor. X squared plus 2x plus 10 is irreducible, so there's no partial fractions thing to do here, but the question is, how do we integrate something that looks like this where we have an irreducible quadratic on the bottom? And so the first step that we need to do is we need to complete the square. The coefficient of our x squared is 1, which means cleaning the square is going to be easier to do. If we have any coefficient of x squared other than 1, we should factor it out and just take it completely out of the problem. But since we have a 1 there, we can proceed. So we take x squared plus 2x, we take half of 2, and we say that that's 1. But we don't have 1, we have 10, so what we need to do is break down that 10 into 1 plus 9. So that's completing the square. And so the advantage of doing that is that now that first three terms, x squared plus 2x plus 1, can be factored as x plus 1 squared plus 9. And this tells us that the substitution we want to apply at the start here is u equals x plus 1. And du will be dx. So on the top of that fraction, I now have 4x, but what's 4x? That's going to be 4 times u minus 1, right? If I take this equation and solve it for x, I get x equals u minus 1, divided by, because it completed the square, the bottom of that fraction is u squared plus 9 du. So that gives us two fractions, 4u divided by u squared plus 9 minus 4 divided by u squared plus 9. This first fraction, we're going to be able to do a substitution. Well, we can't call it u, but maybe we'll call it v equals u squared plus 9. dv is going to be 2u du. And so that's going to be a natural log, pretty simple substitution there. So this will work out to be 2 times the natural log of u squared plus 9. And we'll have to plug back in what u was at the end. But this second integral here, the integral of 4 divided by u squared plus 9, that's a trig substitution problem. So lots of things going on in this one. So the trig substitution we need to do is u equals 3 times the tan of theta. du is going to be 3 times the secant squared of theta. We'll just go ahead and take that 4 out of the fraction completely. On the bottom there, I've got 3 tan theta squared, so that's 9 tan squared of theta plus 9 times 3 secant squared of theta. So on the bottom of my fraction, I have 9 secant squared of theta using my trig identity. 3 divided by 9 is 1/3, so we'll take that 1/3 out of the fraction, and so I just have 4/3 times the integral of d theta, which is 4/3 theta. So that's 4/3. What was theta? Well, u was 3 tan theta, so theta is inverse tan of u over 3. And so that goes right here. So unfortunately, even though we were in partial fractions mode, thinking about polynomials and degrees and coefficients and things like that, we still have to remember all the different techniques that we've learned, including trig substitution. So now the only thing left to do is to plug back in what u was. U was x plus 1. So this is x plus 1 squared plus 9 plus 4/3 times the inverse tan of x plus 1 divided by 3 plus c. And that's my answer there. All right, now let's take a look at this one. So the first thing we might notice if we're thinking about partial fractions is that this is actually an improper fraction. It's really easy to forget to do that step when you're thinking about all the other steps that you might have to do. But when we look at this, we see degree 4 divided by degree 3. So before we do anything else, any kind of decomposition, we've got to do our long division. So we've got x cubed minus 3x squared dividing into x to the 4th plus 2. I'm going to write down my missing powers here with coefficients of 0. Then we say x cubed goes into x to the 4th x times. We multiply and subtract. X times negative 3x squared is negative 3x cubed. When we subtract, we get positive 3x cubed, and then we still have that plus 2. X cubed goes into 3x cubed 3 times. We multiply and subtract, so we get 3 times x cubed. And then 3 times negative 3 is minus 9x squared. And then we subtract, we get 9x squared plus 2. So that means that we can rewrite this fraction as x plus 3 plus 9x squared plus 2, all divided by x cubed minus 3x squared. And now that fraction is one that we can decompose. So we write 9x squared plus 2 divided by x cubed minus 3x squared. That factors as x squared times x minus 3, so we have a repeated factor of x. So that means we're going to write a over x, b over x squared, and c over x minus 3. Again, good rule of thumb is that however many factors you have, that's how many fractions you need. We have 3 factors, x, x again, and x minus 3, which means we need to have 3 fractions, one with x in the bottom, another one with x squared in the bottom, that's how we deal with repeated factors, and then x minus 3, it needs a fraction as well. Now we multiply both sides by that full denominator. Clearing out those denominators gives us 9x squared plus 2, a times x minus 3, plus b times x minus 3, plus c times x squared. Now we can use the plug-in trick partially here. We can plug in 0 and 3 for x. That's going to give us a couple of these coefficients, but then we'll still need to equate coefficients to figure out the last one. So what does x equals 0 give me? Well, on the left-hand side, it gives me a 2. On the right-hand side, a goes away. B gives me 0 minus 3, so that's b times negative 3, and then c times 0. So that's going to give me b equaling negative 2/3. Plugging in x equals 3 gives me on the left-hand side, 9 times 9 is 81, so 81 plus 2 is 83. The a goes away, the b goes away, and then we get c times 3 squared, which is going to be 9c, which is going to give us c is the lovely number 83 divided by 9. And then finally, how do we figure out a? Well, now is when we have to equate coefficients. So we've got 9x squared plus 2. We've got ax squared minus 3ax plus bx minus 3b plus cx squared. So the coefficient of x squared, and there's different ways to do this, but we'll go ahead and use the x squared, is 9 on the left-hand side, and it's a plus c on the right-hand side. So this tells me a plus c equals 9, which means a plus 83 over 9 is equal to 9. 9 I can write as 81 over 9, which means a is negative 2 over 9. So kind of yucky fractions in this one, but don't let those get us down. So we've got x plus 3 plus a divided by x. A is negative 2/9. B over x squared. B is negative 2/3 over x squared. And then finally c, which is 83 over 9 divided by x minus 3. And then we just integrate. Antiderivative of x is 1/2 x squared. Antiderivative of 3 is 3x. That negative 2/9 is just a constant multiple, so that gives us natural log of x. How do we take the antiderivative of x to the minus 2? We're going to add 1 to that power and get x to the minus 1, but then we have to divide by that power. Dividing by minus 1 is the same as multiplying by minus 1, and all that's going to do is turn my negative 2/3 into a positive 2/3. And then finally, we have 83 over 9 times the natural log of x minus 3, and then plus c. So other than the nasty fractions, not too bad. All right, last one. So this is our first example, and the only example we're going to see in this video, but our first example of a repeated irreducible quadratic factor. X squared plus 4 is irreducible, it can't be factored, and we have it repeated, we have it squared. First thing you might notice, though, is at first glance, this may appear to be an improper fraction. We see a cube on the top, and we just see a squared on the bottom. But because that squared is itself squared, the bottom has degree 4. And the top of this fraction has degree 3, which means this is a proper fraction, so phew, we don't have to do any long division for this problem. Okay, so what do we do when we have this repeated irreducible factor? Well, same thing that we do when we have a repeated linear factor. We rewrite this with 2 fractions because we have 2 factors. The first fraction has just x squared minus 4 to the first power on the bottom, and the second fraction has x squared plus 4 squared on the bottom. And because that's an irreducible quadratic factor, we're going to have linear terms on the top, ax plus b for the first one and cx plus d for the second one. Now when we multiply both sides to clear our denominators, we get 3x cubed plus 4. We get ax plus b multiplied by x squared plus 4, and then we just get cx plus d. Now, unfortunately, because we didn't have any linear factors at all, there's nothing that we can plug in here that will easily tell us any of these coefficients. So the only thing we can do is multiply everything out and equate coefficients. So we get 3x cubed plus 4 on the left-hand side. On the right-hand side, I'm going to FOIL that. Ax plus b times x squared plus 4 is going to give me ax cubed plus bx squared, and then plus 4ax, and then plus 4b, and then I still have plus cx plus d. So I'm going to equate my coefficients, and that's going to give me ax cubed equals 3x cubed, so a has to equal 3. Bx squared is the only x squared I see, and there aren't any x squareds on the left-hand side, so b has to equal 0. My linear terms are 4a and c on the right, and there are no x's on the left, no linear terms on the left, so I just have 4a plus c equals 0. And then my constant terms are 4b plus d on the right and 4 on the left, so that means 4b plus d equals 4. So knowing that a equals 3, 4a plus c equals 0 tells me that c is negative 12. And knowing that 4b plus d equals 4 and b equals 0 is going to tell me d equals 4. All right, so we've decomposed our fraction, but we still have plenty of work to do. So we have ax plus b divided by x squared plus 4, so that's 3x divided by x squared plus 4. And then we have cx plus d, negative 12x plus 4 divided by x squared plus 4, all squared. Okay, so how do we deal with all that? Well, this first fraction, we can do a substitution. Because we've got x's on the top and crucially no constants on the top, no constant terms in our polynomial that's on the top, we can do a substitution. U equals x squared plus 4 and du equals 2x. Now we have a 3, we want a 2, so we're going to pull that 3 out as a constant multiple and put in a 2 and a 1/2. That's all going to give us 3/2 times the natural log of x squared plus 4. Now this next fraction, I'm going to actually break that up into two separate fractions. Negative 12x divided by x squared plus 4 all squared, and 4 divided by x squared plus 4 all squared. For the 12x over x squared plus 4 squared, again, we're going to substitute u equals x squared plus 4. We're going to use that x that we have on the top of our fraction to our advantage. That means we're going to have to put a 2 in and a 1/2 out front, which that 1/2 is going to turn that negative 12x into a negative 6. And then we've got 1 divided by u squared, but we know how to integrate 1 divided by u squared. That's going to give us u to the minus 1 multiplied by negative 1. That's going to turn that negative 6 into a positive 6. So that'll be 6 times x squared plus 4 to the minus 1. And I'm saving the best for last here. All right, what about 4 divided by x squared plus 4 squared? Well, no easy substitution is going to work for us there. So unfortunately, that last one is going to have to be a trig substitution. So that's going to be x equals 2 tan theta, because we've got x squared plus 4. So dx is going to be 2 times secant squared of theta d theta. So that's going to give us 4 on the top. I'll actually go ahead and pull that 4 out. On the bottom, 2 tan theta squared is going to be 4 tan squared theta, plus 4 is going to give us 4 secant squared theta, and that's all being squared. And then our dx is 2 secant squared theta, d theta. So that's going to give us, we've got 4 times 2, we've got 8 on the top, 4 squared is 16 on the bottom, so we're going to have a 1/2, which I'll again go ahead and pull out. And then we have 1 over secant squared on the bottom because we have secant to the 4th on the bottom, and 2 of those factors of secant divide out with the 2 factors of secant we have on the top. All right, so how do we integrate 1 over secant squared d theta? Well, we're going to remember that secant is 1 over cosine, so this is really cosine squared theta d theta. And so now we have to take the antiderivative of cosine squared. And we look at that and we probably sigh sadly and remember to ourselves that because we don't have any odd powers of sine or cosine there, our next step is to use the half angle formulas. So that's going to give us 1/4 times 1 plus, we're still integrating, right? We haven't actually integrated anything yet, cosine of 2 theta d theta. Now we can actually integrate something. So we get 1/4 theta. We take the antiderivative of cosine 2 theta, that's going to give us 1/8, 1/2 times the 1/4 that we already had, times the sine of 2 theta. So that's going to be 1/4 theta. So theta, since x is 2 tan theta, theta is inverse tan of x over 2. And what about sine of 2 theta? Well, there we have to remember that sine of 2 theta is 2 sine theta cosine theta. So that's going to give us 1/4 sine theta cosine theta. What are sine of theta and cosine theta? Well, that's where we need to draw our little triangle. We know theta has a tangent of x over 2, so we label a triangle like that. By the Pythagorean theorem, our hypotenuse is square root of x squared plus 4. So we have 1/4. We've got sine of theta, which is opposite over hypotenuse, x divided by square root of x squared plus 4. Cosine of theta is adjacent over hypotenuse, 2 divided by square root of x squared plus 4. So when all the dust settles, we get 1/4 inverse tan of x over 2. And then we've got a 2 and a 4. We can simplify that just slightly. That gives us 2 on the bottom. So we've got x on the top. We've got a factor of 2 on the bottom. And then we have the square root of x squared plus 4 multiplied by itself. So that's just x squared plus 4. And then finally plus c. So lots of nasty stuff happening in this example. And this is the kind of thing that happens when you have quadratic factors, or especially repeated quadratic factors. Trig substitution, some of the nasty stuff that we talked about earlier in this chapter, all rears its ugly head. So hopefully you followed all the steps here and have the tools necessary to approach these kinds of problems on your own. Good luck.